This is part 2 of Unit 5, Lesson 5, Curve Sketching. We're going to continue where we left off with the example 4. So we have the same graph we had for the first half of example 4. And now we're going to assume that the graph below is f of x on the interval -8 to 8. On the same set of axes, we're supposed to sketch and label the graph of f prime. So now we're going to go the other way. So here's some things that we want to notice about our graph. First is that this part of the graph here, f prime of x, is going to be less than 0 because we're going to have a negative slope there. Here we have a horizontal tangent line, f prime of x will equal 0, and this is going to be an inflection point. Because that's where the curve flips over from concave up to concave down. And here we have a max, so that's going to be another 0. And then we have another inflection point here. Which will be where we'll have a 0 tangent line for the derivative. And then we can see here that we have a minimum. I'll go back and fill in some other stuff here. And we have another inflection point here. And the only thing I didn't fill in is here f prime of x is going to be greater than 0. Here it's going to be f prime of x will be less than 0, and then it changes again here. It'll be f prime of x will be greater than 0. Okay, so putting this all together, here is what we're going to have. Now I'm going to erase all this, and I'm going to fill in the important features again as I draw it. So that's my rationale for drawing the derivative the way I'm going to draw it. So using a red pencil, as it says, I know that here I'm going to have a 0. This is still going to be a 0. I'm going to have a 0 here at -1 from that maximum. I'm also going to have a 0 here at this minimum. And then I'm going to make the kind of assumption for the function that that's probably a 0, but I don't want to, be too crazy about that. Okay, so what we're going to have here is the derivative in the first part of the graph is less than 0. So I'm going to come up here to this inflection point here. And I'm going to be, and it helps if I hit the point, I am going to be concave up, and I don't like the way that looks at all. Geez, I'm having real trouble drawing this. There, I like that better. Concave up here. So here my f prime is less than 0, just like it was here. And there is my minimum. I'm concave up. This is my inflection point. And then what happens here is I have to go back to 0, and I'm going to be concave down here. So kind of like that. Maybe not that quite that dramatic. Now I missed it completely. There we go. Okay, so we're concave down. And then here we're going to go down through to our next inflection point, which is there. So we're going to come down here, and that's going to create a horizontal tangent line for the derivative. And then this has to be a 0 at 4, so I'm going to come back up this way. And then I have another inflection point at 6, so I have to have another 0 here. So here's an inflection point. and then it's going to turn around here. So it comes here and it's going to go back down that way. That's about all I can say about that. Okay? So that's what the derivative would look like. Let me get rid of this piece here. Okay? So our concavity is correct based on the sign of the derivative, and where the inflection points are, they would be our zeros of the derivative. So we would have like a non-existent derivative here. If you notice, this is not an inflection point because we didn't change signs here to here. And then here, that inflection point turns into a horizontal tangent line, and same with this point. And here, the derivative of our derivative does not exist. Okay. So part E. Now let's assume that the same graph is the derivative, and then we're going to sketch f of x, given that f of -8 is -2. So that kind of gives us a launching point for our function right here. Okay, so some things we want to look at is that we can see here that if this is the derivative, that f double prime is less than 0. So we are going to be concave down here. All right. And we can also see that the derivative is greater than 0. So our graph is going to be increasing through this section. So let me draw that section. Okay, then we get here, and that's going to be a 0 because it is a 0. We have a horizontal tangent line of our function there. And then what happens is here, this slope, f double prime, is going to be greater than 0, so this has to be concave down from concave up until we get to that point. So this is I'm going to try to exaggerate just a little bit here. Let me erase this so it doesn't get mixed up. So I'm concave out here. I come through here, and I have to switch over to concave down till I get to here. And then I am going to be concave down still, but just kind of like that. I went too far there. Because I do have like a corner here, because I have an inflection point right here, because I'm changing my concavity here. And then I'm going to be like this till I get here. Here's a maximum. This has to be a max because it's a 0 of the derivative. And then I'm going to start to come down. And I have an inflection point right here. And then I'm going to increase again because this slope is positive here. So I have to come down to a minimum to here. Okay, so I went from concave down to concave up. And here's a minimum because I'm going from a negative derivative, and it's going to switch over to positive through here. And then, of course, I'm going to come up like this. And that went a little too far there. So let me try that again. So here's my minimum point, like right there. And then it's going to stay the same concavity like that. Okay, so that's how you kind of go through that. Let me kind of hook these together here. It's hard to draw this with the stylus, so I don't want this little piece. I don't know, let me change my eraser. See if I can just get rid of that little piece there. Okay, so there we go. So there's that one. All right, next problem. So if we want to completely graph from scratch, here's what we're going to do. We are going to start by things that we're very comfortable with. Finding the domain, the intercepts, the asymptotes, and think about how symmetrical the graph is. If it's a polynomial, you can think of things like your end behavior, if you can factor it, if you're finding the intercepts, do they have a multiplicity, things of that nature can also help you. You're going to find the derivative and find the critical points, the intervals where the function is increasing and decreasing. And from that as well, you can determine your relative mins and maxes. And take the second derivative, find its zeros, and help you find the points of inflection and determine the regions where it is concave up and concave down, and then you sketch it. Okay, so let's go through the first function, g of x. The nice thing about starting with one like this is, of course, the fact that we have a polynomial, and it's also already factored for us. So I know that at -2, this function is going to cross over, and at 1, it's going to touch and turn because I have an even multiplicity for 1. So finding the x-intercepts and the y-intercepts, my intercepts are -2, 0, and 1, 0. I have a cross and a touch and turn, and then my y-intercept is going to be 0, 2. Okay, so I have that. Now, finding my derivative, there's two ways you could do it. It's not a terrible function. If you want to multiply it out and then just use the power rule, you can. What I did was I used the product rule for the first derivative, and then I multiplied it out and used the product or the power rule for the second derivative. So that's what I'm going to do, because the chain rule for this is really simple. So, but if you want to multiply this whole function out, you can do that. G prime of x is going to be x minus 1 squared plus x plus 2 times bringing the power down, lower the power by 1, take the derivative of x minus 1, which is 1. So this gives me, I multiply this out, x squared minus 2x plus 1, and then the second part gives me plus 2x squared plus 2x minus 4. So g prime of x is then 3x squared minus 3. The x terms cancel because you have a minus 2x and plus 2x. So then g double prime of x is just going to be 6x. Okay, so now what we need to do is find our critical numbers and our possible points of inflection. So I'm going to set my first derivative equal to 0 here. So 3x squared minus 3 equals 0. Gives me an x squared equal to 1, so x equals plus or minus 1. These are my critical numbers. Okay, and then I'm going to set my second derivative equal to 0, and I get x equals 0. This is my point of inflection. All right, so now I can do my sign chart for g prime. So making a sign chart here, I have my sign of f prime and my f direction. I have two critical numbers. I have -1 and 1. So I'm going to check x equals -2, x equals 0, and x equals 2. So when I put those numbers individually into my derivative, I put -2 in, I'm going to get a positive number because I'm going to have -2 squared times 3 and then minus 3, so that'll definitely be positive. So the function is increasing there. I put 0 in, I get -3, so the function will be negative or decreasing because the derivative is negative. And then when I substitute 2 into the derivative, I am going to again get a positive number, so the function starts increasing again. Okay, then determining any relative extrema, I can see here I have a relative max and a relative min there, and I'm going to substitute the -1 back in my original function. So I have a relative min at 1 comma, so I'll get 3 times 0, so I get 1, 0, and a relative max at -1, so I'll have 1 times -2 squared, so 1 times 4 is 4. Okay, so I'm doing good. All right, next thing. I need to do a sign chart for my points of inflection to determine the concavity. All right, so here I have 1, 0. So here is going to be my sine of f double prime and my f direction. Okay, so I'm going to do -1 and 1. So when I substitute -1 into my derivative, that's pretty simple because it's linear. That's going to be negative. So I am concave up. And when I put 1 into the second derivative, I get a positive number. So I'm concave down. So any point of inflection, that is definitely going to happen at 0. So if I put 0 in my original function, I am going to get 2 times 1, so I get 2. So my point of inflection is at 0, 2, which is also the y-intercept. Okay, this is actually a very symmetrical graph. So we have, let's put everything on that we know now. We have a y-intercept at -2. We have I'm sorry, that's an x-intercept. We have a y-intercept at +2. We have an x-intercept at 1. Now what we know is, seeing our sign chart here, that we have a relative max at -1, 4. We have a point. And we have a relative minimum at 1, 0. Which we would expect, because remember we said that it should touch and turn at 1. Okay, so the graph is increasing before -2. It comes up to its maximum, turns around, comes down. This is like one of the worst graphs I've ever drawn in my life. Turns around, touches and turns there, and goes back up. Which I had already assumed it would look like that, just knowing everything from what we did in pre-calc, is the fact that this is cubic and the leading coefficient is positive, so its end behavior would be like this, that I would cross the x-axis at -2 and I would touch and turn at 1, and that's exactly what happened. Okay. I'm going to stop this video here before it gets too long, and I will finish up our curve sketching in part 3.